So I'm going to look at this Pine Valley company. Actually, yeah, let me show you this actually. Just a second. Yeah, so actually, if you go to the Blackboard and where is it? Oh, yeah. So if you go to the course content on the left navigation bar, then here I uploaded this sample case study, Pine Valley Furniture Company. So if you look at this, there are some scenario of this company basically. It's like a furniture company, and there is some history about it, and it has some information about what this company is doing. So basically, if I go through briefly, the Pine Valley Furniture Company manufacture high quality wood furniture and distribute it to retail store within the United States. So basically, it's like some way it's like IKEA. So they make some furniture and sells, and its product lines include dining table, like dining set, and stereo cabinet, wall units, and living room furniture, bedroom furniture like this. And in the early 1980s, Pine Valley Furniture's founder Alex started to make and sell custom furniture in his garage. So he started from his garage, this business. And Alex managed the invoices and kept track of customers by using file folders and filing cabinets. So when he started his business, there was no IT system. So database system, he doesn't even think about it. So there was no IT system. He did everything manually by hand. So he recorded everything by hand, and by 1984, business expanded. So Alex had to rent a warehouse and hire a part-time bookkeeper. So still, he's using bookkeeper. PBF's product line had multiplied, sales volume had doubled, and staff had increased to 50 employees. And by 1990, PBF moved into its third and present location. Because of the added complexity of the company's operations, Alex reorganized the company into the following functional areas. So there are multiple areas in this company. So that means basically there are multiple potential business case. One is manufacturing, sales, order handling, employee management, and purchasing raw material. So there are multiple business events that uh, happening in this business scenario basically. So Alex and the heads of functional areas established the manual information system. So now they are using information system, such as using spread, basically Excel file. Yeah, basically he's using Microsoft Excel, something like that. So which worked well for a time. Eventually, however, PBF wanted to automate the process and organize its data better. So now they are not satisfied with using the something simple tool like Microsoft Excel. So later, PBF formed a task force to study the possibility of moving to a database approach. After a preliminary study, management decided to convert its manual information system to such an approach. So now they are considering a database approach. So the database system should support capturing managing data from each business process. When customers order furniture, their orders must be processed appropriately. Furniture must be built and shipped to the right customer, and the right invoice made to the right address. Employees have to be paid for their work. With the new centralized database, data should be organized around the entity subjects, such as customers' invoice orders. So like basic information. So Pine Valley Furniture Company decided to develop its own database system, and it hired staff and brought both computer hardware software necessary. And let's just see how a product manager plays a key role in this one. So basically, they decided to develop database system, and we have to help them, right? So the question is this: propose a database design for Pine Valley Furniture Company by doing the following. So first of all, we have to identify business events and business rules. So business events, I think we can think about these things: manufacturing, sales, order handling, employee management, and purchasing raw materials. So basically, it's kind of all the things they are doing. So they buy some raw materials and they make furniture, and uh, basically they are selling it, right? So there should be sales and customer orders. Then we have to handle the order, and also they may have to manage their employee. So in the database system, it should be able to store information about this and it should be able to handle all these things. So we have to identify business events, and we have to infer following business rules. And we have to provide conceptual ER diagram for the proposed business events. So for each of business event, we have to do the conceptual data modeling to create a conceptual ER diagram. And then we have to provide a relational model based on integrated ER diagram. So that's what we want to do here. Okay, so basically, we already looked at the company's background at the Blackboard, and let's check the major business events. So basically, they have manufacturing, sales, order handling, inventory management, and purchasing raw materials. So those are major business events that can happen inside this company. So the next step is this. For each of a business event, we have to infer the potential business rules, and we have to document it. So the question is simply giving like a basic guidance and these kind of things, basically is letting us to do. So for each of the business event, let's just think about some rules, like what kind of things can exist and what kind of rules we need. So first of all, let's just think about manufacturing business event. So what kind of rules that may exist in this process? So the first is this. It's basically the process of making product from the raw materials, right? So product is made of one to many raw materials. So that's one of the business rules. And the second one is this. The each raw material can be used in at least one but many other products. So if the raw material is not used to make a furniture, the company doesn't need to buy it, and the company doesn't need to have the information about it. So only when the raw material is used in at least one product, we need to keep this information. And there are multiple manufacturing facility. So there are multiple facility because it's not just in his garage anymore. It expanded his business in multiple locations. So there should be multiple facility, and each facility can make many different products. So some facility is specialized into something, and another facility may be specialized into something. So basically, each facility, but they can make multiple products, and also product can be made in any of these facility. So the same product may be made in different facility too. And the first thing is this. So when we have this business rules, we have to identify what will be entity to keep the record of the data. So first of all, we are talking about the product. So the product is main thing, and also raw materials. We are talking about the relationship between product and the raw materials. And then there's also facility here. So which product is made from which facility, something like that. So basically, from this business rules in this business event, we are able to identify three main entity. So we can create that. So product entity should be here, and the raw materials. So we have that entity here, and also facility here. And then we can create the attribute which will be appropriate to represent the information of each entity. So for the product, we can have a PID, which is a product ID, as a primary key, and we can have a product name. And for the raw materials, we can have a MID, which is a material ID. And then material name, we can have that as an attribute. And for the facility, we can have a FID, facility ID, as primary key, and the location maybe as attribute. And then we have to think about the relationship. So first one is a relationship between product and the raw material. So it's made of, so we can use that. So made of relationship is between product and the raw materials. So basically, a product is made of one to many raw material. So from the product's perspective, it can be made of one to many raw material. So that's the cardinality. And from the raw materials perspective, it says that each raw material can be used in at least one but many other products. So at least one, many other products can be using these raw materials. And also here, we can put like a quantity required. something like that. So what it means is this. So to make a table, you may need for wood and like I don't know 10 nails or something like that, right? Then to make a table, we need this, like this is a product and this is a raw material. So to keep track of this number, we can add the quantity required here. So when for a certain product, for a certain raw material, how many of them we need. So we can keep that quantity required here in this attribute, and that can be saved inside this made of many-to-many relationship. And between product and facility, we can have this made in relationship. So each facility can make many different products. So from the facility facility's perspective, at least one many products. If there is a facility, then it should create at least one product. So that was my assumption. And from the product perspective, product can be made in any of these facilities. So maybe there should be at least one facility that makes this product, and many other facility can also make the same product, like a table. So yeah, that will be a sample ER diagram for this business event. So I mean, you can also add more things. So yeah, Derek said like a bill of materials. So currently, I didn't include it here, but also um, yeah, this is a manufacturing business event. But when we talk about like purchasing raw materials, that kind of business event, we can have like a bill of materials too. So if you think, so basically it's depending on the business rule, what you define. So even though, let's just say that even though I ask you to, I give you like a business event of manufacturing, depending on what you think as a rule, and depending on what you think is more important, the business rules will be different. So what you document here as a business rules will be different. And if business rules are different, the entity you infer and the relationship you infer will be different. So that's why it will be like an open-ended question, more like a project style. So this is my sample answer, but also you can design it differently, depending on your assumption and depending on your rules and depending on what you think is more important in this case. And the next one is sales. So customer makes an order and the company should sell their product. So it's about that. So a simple rule is this. For the sales business event, we can say that customer order furniture product. So we have a customer and the product again. And each order can contain multiple products. So order contain multiple products. And customer belong to a certain sales region. So basically the region, right? Sales area. And each sales region contains multiple customer. So we can, this is the same thing. So we can identify 1, 2, 3, 4 entity from this business rule here. So basically, in this case, we can design those first. So customer put it here, and customer order furniture product. So the product can be ordered furniture product. Each order contains multiple products. So we can put the order first. And the order contains multiple products. So product is here. And customer belongs to a certain area, so region is here, like this. So customer ordered multiple furniture products, but in this case, we don't need to make a direct relationship between customer and product because it's more like a customer makes an order, right? So actually order should be entity here. So customer makes an order and order contains products. So that's a more correct relationship. So customer will place an order. So if we think about the cardinality, for each customer, how many order can they make? So they can make many order, let's say including 0. Let's say that they made an account in the website, but they didn't make any order, then it can be 0. And if the order is here, from the order's perspective, how many customer can make that order? It can be only one by one. So for each account, they basically, if there's an order, it should belong to a certain account which made that order. So it should be one by one. And order can contain multiple products. So when customer makes an order, it doesn't need to be about one product. He can order, basically, he can include like 4 tables and 1 cabinet into one order. So that's possible. So basically, order contains products. And from the order's perspective, each order may contain at least one product, but many products. Okay, yeah, I show you the solution again a little bit later. So once you're tasked, so I'll show you that again. Yeah. And from the product's perspective, each product can belong to multiple orders. So let's say that the product is not that popular, then maybe nobody ordered it, then it may not belong to any order, but potentially many people can order the same product. So it's zero and many. And also earlier what I said is this. So customer makes an order, and order may include like 4 tables and 1 cabinet. So that's also possible. In that case, we need to store this number, how many quantity ordered. So that can be stored in this many-to-many relationship. So we can store quantity ordered here, like this. So that's it. And the next one is customer belongs to a certain sales region. So belongs to relationship, or you can say live, whatever you want. So customer live in some area. Each customer belong to a certain area. So yeah, physically a customer should belong to one and only one location. And each location may contain many customers, including at least one. Let's just say that. So if the company is doing like business in a certain area, then I expect that there should be at least one customer. I mean, it's okay to be zero. It doesn't matter in this case. One thing I forgot is attributes. So there should be customer ID as primary key, and name, and many other customer information we can store. Let me skip that. For the order entity, we can have OID, order ID as primary key, and something like order date, we can have that. For product, product ID can be the primary key, and we can have other things too. And the region, I think product, because we already defined it here, so I skipped that. And for the region, we can have the region ID as a primary key, and the region name or location name as an attribute, something like that. So this will be sample conceptual ER diagram that I can infer from this business event. So direct question is this: we could have built a ternary relationship between customer, order, and product. Yeah, let's let me think about that. Ternary relationship between customer, order, product. It's possible. It depends. So it is possible, I would say. But depending on the situation, it may not be that efficient. The reason is this. Let's just say that I think it's better to use the whiteboard. So let me. Yeah. By the way, this is the previous manufacturing. ER diagram for the manufacturing business event. So you can take a screenshot if you want. Okay. So for this one, let me actually show you about this. Okay, so yeah. So what Derek asked is whether we can build a tonal relationship between customer or the product. So there's a difference in that design actually. The reason is this. It's because there's many too many relationship involved here. So in that case, so earlier when I showed you tonally one-to-many relationship and tonally one-to-one relationship, we can separate them into binary relationship. That's possible. But when you have many too many tonal relationship, if you separate them, the design is actually changing. So what it means is this. So we have a customer, order, a product. And I made this relationship, customer. Uh, Let me just simplify this. So something like this. So we have this. Then basically when we implement this, what's happening is this. When we implement this into the relational design, then we have a primary key here, CID. And for the order, we have a primary key here, OID. And for the product table, we have a primary key, PID. And this will become assignment table. So here we have a primary key, OID, primary key, PID. And if we have a quantity here, the quantity will be added here as a attribute. So that's what we can expect. This is an assignment table. And then if you think about the other relationships, so basically here we'll have a CID as a foreign key because it's one-to-many relationship. So CID will be placed here. However, so that's one possibility. However, if we let me put it here. If we make a tonal relationship between customer, order, and product, like this, then for a certain customer, for a certain order, there are many products. For a certain customer, for a certain product, for a certain customer ordering certain products, there can be included many products. For a certain order, basically for a certain product in a certain order, there should be only one customer. Yeah. It should be something like this. Then when you implement it, what's happening is this. So see, um, so basically we'll have a customer table with the primary key, CID, and we'll have the order table and product table. So order table will have a primary key, order ID. Product table will have a primary key, product ID. And then this will become assignment table. So we'll have assignment table here with the primary key, OID, primary key, PID, and foreign key, CID. So foreign key will be added here instead of here. So here foreign key for the first design, which I showed, foreign key will be added inside the order table, but for this tonally design, foreign key will be added into assignment table. So using this information and using this information to join with this table, actually this design works. So if you try to calculate some information and retrieve some information, this tonally design also works. However, in some cases, it may not be that efficient because of this. Let's say that we want to find, let's say that there is a customer, for the customer ID 1, we want to find how many orders he placed, how many orders he made. So we are curious about that. Then we'll design a query for that, right? And then in the first design, we can simply utilize this information, these two tables. So we can do the join between these two, and for each customer, we'll know we can do aggregation query and we can count how many orders placed by each customer. So for this one, we have to, let me think about it. So for this one, we have to join. Then because of this, there will be multiple, there will be some duplicate information if you do aggregation. So you have to use I think you also have to use like a distinct operator. Yeah. So the query will be more complex basically. We can just use these two tables to calculate this information, but because because there might be multiple products in each order, the same order information will be displayed multiple times. So we have to use a distinct operator when we design aggregation query. Basically, we have to also utilize a subquery in this case. If I didn't check it, but if I think correctly, you also have to use a subquery, and inside the subquery you use distinct, and the main query will be aggregation query. So this will be more complex in that kind of a scenario. So this design works, but I think there is some difference between these two. So Derek said something else. So let me see. We need another relationship between order and product to store quantity ordered. Between order and product. Where for this design, quantity can be here, and for this design, actually we can put quantity here inside here, because CID is a foreign key, so we can simply put quantity here too. So I think it's fine. No need to design additional table in this case. It is better for us to bear in mind the query work required when we design. So for the midterm, it's okay. For the midterm, I'll give you more flexibility, so you don't need to worry too much about it. But in the real world, in the practice, when you design, basically when you do conceptual data modeling, it is good to think about what kind of query you will need to. That's also that will be like a kind of good mindset to have when you like work on this kind of technical stuff. So that would be my answer. And especially later we are talking about big data modeling. For the big data modeling part, it is necessary. It is necessary to keep in mind of what kind of query you will design in the future. Because in the big data part, the processing time is more important because the data size is much large. But relational database is less important, but still it's good to keep that in mind. Okay, so I hope this gave you some idea. In the midterm, you don't need to worry too much about it, but in the practice, this will be important. Okay, let me put this like this. Okay, so so this is a sample answer. If I do this, and the next one is this order handling. So so let's look at this. So order handling, basically order will be handled by a salesperson, which is employee. So that is the main thing this question is talking, or this business event is talking. So for this one, I can infer this business rule here. So basically, order is handled by a salesperson, a single salesperson. So there is a dedicated salesperson for every order. Each salesperson belongs to one sales region. So salesperson belongs to also a region, and the invoice is generated. So invoice is generated by the salesperson and shipped to the customer. And invoice include total price, amount paid, and balance due, some additional attributes. So basically, because invoice contains multiple information which belongs to that invoice, so that's why we are going to create invoice as an entity in this case. So for the entity, we can have order, salesperson, and invoice. and the last one, the region. So we can have this for entity here, and let's think about the attribute really briefly. So order may have order ID as primary key. Salesperson is employee, so we can give employee ID as primary key, and office and probably like name or something like that, other information. Region, we had this earlier, so region ID as primary key. Invoice, we can have a invoice number as primary key, and these three attributes like total price and the amount paid, and we can have like a balance due, something like that. Okay, and the next one is a relationship. So order is handled by a single salesperson. So basically, we can create handle relationship between order and salesperson. From the order's perspective, there should be one dedicated single salesperson. So every order should have one salesperson. And from the salesperson's perspective, so salesperson will deal with many orders. So they may deal with many orders, including zero, if he hasn't dealt with any order. That's also possible. Yeah, the next one is now each salesperson belongs to one sales area, so we can create the belongs. So salesperson, they should belong to one sales area, so one and one, and each area may have multiple salesperson, including one, like this. Okay, so and the next one is invoice. So invoice is generated by salesperson and shipped to the customer. So we can create generate relationship here. So invoice is generated by salesperson and shipped to the customer. So basically invoice is about a certain order. So basically we can create like this. So here my assumption is this. There should be one invoice for each order. So I can create this ternary relationship here. And for a certain order, so basically here, to define the cardinality here, we have to think about from the perspective of a certain order by a certain salesperson. So certain order by certain salesperson, there should be one and only one invoice. If I assume that there should be only one invoice for each order. And here from the order side, one from the perspective of an invoice by a certain salesperson, there should be one corresponding order. And from this here, from the salesperson side, from the perspective of a certain invoice of a certain order, yeah, it should be sent prepared by one salesperson. So I can put one and one. So basically, it's one-to-one relationship. So you can also create separate binary relationship for this case. Yeah, so that's all. So that's all for conceptual ER diagram for this business event based on this business rules with some assumption. Okay, so let me go to the next one. So I received also more question about the previous one, but about related to the query. But let me answer separately later because there's also time limitation of this course. So okay, so let me go to the next one. Okay, so this one now employee management. So we can have you can infer this kind of rules for employee management. So employees can be salesperson. So we had a salesperson and worker. Worker is who basically makes the product. And one employee can supervise many employees. So we can have basically it's the between employee and employee. So it's a unary relationship. And each employee can be supervised by only one employee. And a worker works in one manufacturing facility, and one facility can have many workers. So for this one, basically we needed to have employee, worker, sales person, and facility. So we can create these four entities here, and for the attribute, we can have an employee ID as primary key for employee, and we can have a name. And for worker, we can also have employee ID, and we can add some like wage rate information. For sales person, we already created this earlier, so we had the EID and the office information or something like that. And the facility, we can have a facility ID, and we had the location earlier, I think. So the relationship is this. Employees can be a salesperson or worker. So we had a similar thing in the assignment one. So we can have each relationship. And in assignment one, I made two binary, but here I can just use ternary. There's no difference between them. If it is a 1-to-1 relationship. So we can have this ternary relationship. Basically, employee might be worker or salesperson, and if they are salesperson or worker, it should be employee. And then there's a supervised relationship. Basically, we can create supervised relationship here. So one employee supervise another employee like this. So one employee. So from the employee, basically it's just the supervisor and supervisee. So we can consider these two. So from the supervisor's perspective, they can supervise many employees. So many, including zero, maybe if I don't supervise anyone. And each employee can be supervised by only one employee. So from the supervisee's perspective here, there should be only one employee who are supervising me. So one and only one. So that will be one-to-many unary relationship. So we can create that here. And it's a works relationship, the last one. So worker work in facility. So worker works in one manufacturing facility, so only one. And one facility can have a many worker, including one. So we can design a conceptual ER diagram based on this business event and business rules like this. So that's it for this one. And let me go to the last business event we have here. The last one is this, purchasing raw materials. So now company also want to keep information about which vendor they purchase this material. So we can have this simple business rule. Then a vendor provide one-to-many raw materials, and like this. So basically we have two entity here. Supply relationship between these two. For the attribute, yeah, forgot about that. So attribute, we can have vendor ID, vendor name. For raw material, we made this entity earlier. We had the MID, material ID, and the material name. So for this relationship, it's basically relationship between vendor, supply, raw materials. So from the vendor's perspective, vendor provides one-to-many raw material. So at least one, many raw material. From the raw materials perspective, each raw material can be provided from one-to-many vendor. So we can have this many-to-many relationship here. So that's it. I mean, we can put more if you make more assumption, and if you put more business rules, then actually you can put more things. But let's just provide a simple conceptual ER diagram here as like a sample example. So we can make this simple conceptual ER diagram here. So the thing is this. So after you create and design conceptual ER diagram for each of the business event. The last step is combining them together to create integrated ER diagram. So basically, there are common things. So we have raw materials here, but we also had that earlier. Then we can combine them together. So here, let me see. We have a salesperson here, same salesperson is here. So basically, it's the same entity. So we can combine them together. And then eventually we'll have something like this. So I put this here on the slide. So we'll have an integrated ER diagram. So basically, customer belongs to some area, it's here, and customer place order is also there. And also earlier the salesperson appeared in multiple business event. So salesperson is employee. So that business event is here. And salesperson generates invoice. That business event is there. And salesperson belongs to a certain area. That business event is there. So basically, we are putting the common things together to create and combine all the business events to come up with the integrated ER diagram. So that's the last step of the conceptual data modeling. So once you have an integrated ER diagram, the next step is simply translating this into relational model. So in the next page, I put this relational model. So basically, based on this, if I translate this into relational model, it will be something like this. And I simply make this in the MySQL ER diagram editor, and then I can use the fold engineering to implement and to have the database implemented in my server. So that's it. So then implementation is done. So once the implementation is done, what you need to do is that basically insert the data, right? So if you have some data, you can insert it. You can insert some sample data, and then the next step is just simply design, suggest some useful query. So based on your design, based on what you implemented, you can think about and you can come up with some query suggestions. So that will be also part of the midterm. So I will not give you like a specific query you have to design, but you can come up with some idea. And then based on your idea, you can propose some potential query which might be useful. So if we think about like 5 queries which may be useful in this case, is something like this. So first of all, we can design the query which list all the customer information. So that can be like a simple query, right? So this is a simple select query. And another query you can think of is something like this. List all customer information together with sales region where the customer live. So basically, customer belongs to and live in a certain sales region. So you can design a query that shows this information together. So customer information and where they live. So this will be basically also select query. It will be simple select query with join, because you have to utilize 2 different tables. And another query you can design is something like this. For each sales region, count the number of customer living there. So basically, we want to know how many customers we have in each sales region. Then we can design this query for each sales region, count the number of customers living there. So for this one, basically we have to utilize the aggregation. So it's aggregation query. And number 4, another query we can think of is something like this. So we covered this in the one of the example earlier. Basically calculate total price each order, or maybe invoice too. So for this one is aggregation also, and also you have to utilize a join, I think, to calculate total price of each order. Yeah, aggregation join. Yeah. Yeah, because the price is inside. Yeah, product. Okay. And another query you can think of is something like this. Instead of select, you can also think about update query. So update total price field in invoice entity. By using query number 4. So query number 4 is calculating total price of each order or invoice. And we can use that query. So basically we can put that query as a subquery, and we can design update query, which is updating total price field in invoice entity or order entity. So that can be another query which utilize update and subquery.